Good morning, everyone, and thanks for attending. My name is Eric Weber, and I'm an application engineer here at Linux, and today I'm going to give you an overview of some of the additional capabilities of SOLIDWORKS simulation beyond linear static and basic motion studies that allow us to predict product performance early in the design process, which in turn helps us cut costs, reduce time to market, and also maximize quality for our products. So the some housekeeping things here. If you can kind of see the picture on the left, there is a box for questions. It allows you to enter in some questions that we can answer during the presentation. Otherwise, we'll cover those at the end of the presentation. I've left some time to do that, so I have some assistants kind of monitoring that, and they'll interrupt me if any of those questions arise. So again, we'll try to answer those throughout the webinar if appropriate, but we can also answer or take some more questions at the end. And then also note, today's presentation is being recorded and will be provided to you guys. So today I'll be using this PowerPoint presentation that gives a general overview of the capabilities of the SOLIDWORKS software, SOLIDWORKS design validation product software. So I'm actually going to focus on simulation here, and this will give us the general overview as well. I've put together some examples that I'll show you actually inside the SOLIDWORKS simulation software. So as most of you already know, SOLIDWORKS simulation allows us to run linear static analysis and motion analysis. So the main difference between these two is the type of solver that is used. So the linear static solver allows us to investigate deformable bodies. These are simply bodies that can deform or change shape under some loading case. So this type of analysis allows us to predict things like deformation, stress, and reaction forces of a structure. We can also run basic motion studies to investigate rigid body dynamics to help us with motor and actuator design. So the rigid body motion solver assumes that the bodies are rigid and cannot deform under loading, so they can't change shape under loading. However, the forces are still transferred from body to body. So beyond these basic capabilities that are included at the SOLIDWORKS premium level, which is our SOLIDWORKS simulation, the first level of SOLIDWORKS simulation. Beyond these capabilities, we have Simulation Professional and Simulation Premium that each give us additional study types that we can run. So today I'll focus on Simulation Professional, but we'll cover Simulation Premium at a later date. So if I click here on the Simulation Professional button, you'll see that what's included within each of the packages. So I mentioned that we can run linear static analysis for assemblies and also basic motion analysis. And again, these first two capabilities of simulation are actually included at the SOLIDWORKS premium level, the highest level of SOLIDWORKS. But additionally, we can add on Simulation Professional and Simulation Premium to any seat of SOLIDWORKS. So let's first kind of review what we get at the SOLIDWORKS premium level, which it sounds like most of you are currently at. So linear static analysis allows us to set up loads or restraints and then a load case that allows us to predict how the body or structure will deform. So in this case, you can see we're kind of showing a stress plot that's animated under some load case. So again, the static studies can check for stress and displacement for a performance and quality check. This helps us avoid failure and decrease over-dimensioning. So we can check different design changes, maybe change some dimensions, and allow us to, and then quickly simulate those and allow us to see how it will perform. So this allows us to, again, calculate the stresses and factors of safety calculations that are included in the software, so we know that our design will perform the way we expect it. And then on the motion side, the motion analysis, again, it's a rigid body solver, and it allows us to set up our assemblies with different motors and actuators. And this allows us to, plot things like displacement, velocity, acceleration of things like, for example, at the end of this arm, we can calculate what the velocity, acceleration, and displacement is, and also trace the path of where it will move. So to just kind of review some of the linear stacks, I want to jump over to SOLIDWORKS and just show you kind of the example I'm going to be using throughout the webinar today. And this is actually a framework that sits beneath a cab on a piece of construction equipment. So this frame supports the cab, which is which has some weight, and you'll notice that the cab is missing from this analysis because one of the main things we always try to do in simulation is to try to reduce our assemblies down and make those as simple as possible, but not too simple where we're not getting accurate results. So the first thing with any setup of static analysis, of course, is to create our study, and here I've created a static study and set up the different parts that we have in our study. So I have about 10 parts here in this assembly, and you can kind of see it's mainly just this frame structure made of mostly sheet metal parts. You'll also know that you'll also see that I have a material defined for each of the bodies. Now in this case, everything's made of plain carbon steel. But with SOLIDWORKS simulation, we are able to apply any material property that we want to any of the bodies in our study. In this case, we'll use the plain carbon steel. And then, of course, when we have an assembly, we need to set up, we need to tell the software what parts are connected to each other and how those will react, parts that are adjacent to each other. So you can see here that my global contact is a bonded contact, which just means that everything that's initially touching face to face will actually be they will act as if they're welded together, so they won't move relative to each other. There's some additional contacts that were set up using the automatic contact detection, which basically detects all the edges, edges of the body. Because this is a sheet metal part, there were some weld gaps, so I was able to go in and pick, add some additional contacts. And again, these are all just bonded contacts, just making sure everything is connected there. So then the next part is to set up our fixturing system. So this frame actually sits on an arm that actuates it. It moves up and down, so the operator of the machine can step into the cab off the ground. There's no ladder to climb, so it's a safety feature that this company has put together. And for the fixturing, what I've done is I've just fixed these cylindrical faces and edges where this frame would connect to the actuating arm. So we're fixing those with geometry that prevents any axial movement or radial movement of these circular edges, but we are allowing rotation of those edges, so they can sort of twist. But again, with linear statics, we need to make sure everything's in static equilibrium. So we need to fix everything in all of our degrees of freedom. So in the X, Y, and Z direction, we cannot have any translation. So fixing these components and having those bonded contacts kind of holding the structure all together, that allows us to run a static analysis, because our body, our total structure is fixed in space. So then next is to apply our external loads. In this case, I have a remote load with some different, if I edit this, you'll see we have some different force values in the X, Y, and Z direction shown here. And those are just applied at the load input coordinate system that was created beforehand. So that's actually the center of mass of where the cab would sit. Okay, so we're applying that remote load. And then we also have a gravity load That's a little bit higher than gravity itself. It's about 1.6 Gs. So this sort of simulates a load case where this thing is moving in the upward direction. Okay. So once we go through and set this up, and I quickly went through the setup, what we can do is we can run the analysis, and again we can find things like stresses. So if I show my stress plot, you can see that we get kind of the highest stresses here in this corner. So we can look at stresses as well as displacements to sort of see how things are deforming. These plots can be animated, so we can see how they're sort of deforming as that load gets applied. So as those forces act kind of down in the negative y direction, we do have some additional forces in the x and z direction, but most of it's occurring in the y direction. So you see kind of this the end sort of drop down, where we can see a maximum displacement of 0.193 inches. We can also plot factor of safety. So if we're looking for a factor of safety of 2, it appears that this is just beyond that factor of safety of 2. But we can see sort of everywhere else we've got a very nice factor of safety beyond probably about 5, sort of everywhere else other than in the corners. So those are definitely places that we'd want to investigate further, probe, and actually see what those values are. So that's kind of an overview of linear static analysis. Now, in motion analysis, again, both the static and the motion analysis are available within SOLIDWORKS Premium. But once we go to the simulation professional level, now we've opened up to some additional study types that we can run. So the first I want to cover is the event-based motion. So event-based motion is very similar to it's very similar to the basic motion capability, where we can use things like motors and actuators to set up motion of our devices or machines. But with the event-based motion capability, we're allowed to set up events that can be triggered with time or sensors that sort of trigger the next event. So you can see with this machine, we've got kind of this arm that's going and picking up a vial, moving it, putting it in the turntable, and then you see the turntable rotates, and then it continues on. It goes and picks up a second vial, drops it into place, the turntable moves. So you see there's a lot of different events, there's a lot of different motors that are working in conjunction with each other. So event-based motion allows us to set up these triggers and look look more at the timing and allow us to calculate things like accelerations and velocities of our components to try to reduce cycle time for the machine, and also obey the limits, the acceleration limits that different electronic components can move. Another example would be on this piece of construction equipment where we've got the arm lifting as well as the cab sort of rotating, and you can see here we're actually plotting we're plotting the motion of the arm as well, so we can kind of see the displacements. We can see the displacements being plotted along with the study. So within our motion study, again, this is our rigid body solver. So this allows us to look at things like the rigid body dynamics, so displacements, accelerations, velocities, and reaction forces of our rigid body assemblies. So we can do our time-based motion simulation and our event-based motion simulation within Simulation Premium, again, helping us with sizing of motors and actuators. We can understand power consumption of motors, what sort of power we need, optimize springs and dampers. We can simulate cam drives and latch mechanisms, investigate gear drive motion, calculate contact forces between these rigid bodies. And then also we can take any kind of snapshot in time of our motion study and actually do a stress analysis at that snapshot in time, do a linear static analysis with the external forces that are acting on a single body. We also have the capability to do motion optimization, where we can set up different parameters such as dimensions or materials of our and also motors of our different of different parts in our assembly, and then we can run through and analyze maximum acceleration and try to minimize or maximize different results. So that being acceleration, velocities, forces, things like that. So for the remainder of the webinar, I'm going to actually be covering the deformable body solver. So that's typically known as FEA. It's a term that may be used. So for FEA, we're using that solver to do our linear static analysis, our frequency study, fatigue study, buckling, pressure vessel, thermal, drop test, and then some of these additional tools like 2D simplification, optimization, and submodeling, which are an extension of these other study types. So within deformable body mechanics, there's different types of failures that can occur. The first is yield failure, which means that the stress value of a material gets to the yield stress value, or under a load case, the stresses get to a stress value of the yield of the material. So if we go beyond that yield value of the material within our load case, the material will permanently deform. So the forces get so high that the material won't deform back to its original shape. So that's usually the first point of failure that a lot of companies design to. So linear static analysis can do that just fine. Now another type of failure is fracture failure, which actually occurs at a stress value above the yield stress of a material. So fracture occurs at the ultimate stress of the material, and this really can only be covered with the nonlinear solver, because what happens is once you get beyond that yield limit of the material, we actually have the stiffness of the material will change and become nonlinear. So we need to actually use the nonlinear solver to solve for fracture, and that can be done with simulation premium. But some of the other types of failure in deformable bodies is fatigue failure. So fatigue failure occurs when we have multiple loads, or a very high number of loads, a high number of static loads. So a load that occurs and then is turned off. A load that happens then goes off. So any cyclic loading case would be an example of fatigue failure. So if we explore fatigue failure, you can see here that the need for fatigue are, again, a load case, which is basically just a linear static study that we set up, and then also the material SN curve. And what the SN curve tells us is the number of cycles to failure at a specific stress value. So this can be done with some lab testing. We can obtain an SN curve and input that into the software along with our linear static loading case, and then tell it how many number of cycles to run, and we can kind of see what our damage percentage is in any location on our model. So a damage percentage of 100% means that we would have fatigue failure, where the number of cycles that we've applied is actually over the number of cycles that location can take based on the SN curve. So again, fatigue studies will predict how long a product will last. This is generally tens of thousands to millions of cycles of load cycles. So we can modify our existing design to extend working life of it. So we can we can make design modifications and of course increase the product life. So again, this is performance under cyclic loading. We can do both a constant cycle or a variable loading cycle where the amplitude of the loads changes as the load load history occurs. So we can set up this variable loading history as well, and also import this load history from physical tests. We can also set up multiple load cases. So let's say you have maybe a thermal cycle as well as just a static loading cycle. We can include both of those studies in the fatigue study and combine those stresses from each study and actually apply that to the fatigue study as well. Okay, and then what this takes is the SN curve for the material, and this helps us identify those critically damaged areas. Okay, so I'm going to jump back over to SOLIDWORKS and just quickly show an example of the fatigue study. So within our fatigue study, again, this is based off of a linear static study. So if we look at my loading folder here, you can see that I've got this event set up. So if I edit that event, we can see that I'm loading this for 20,000 cycles, and we've got a fully reversed study, meaning that our load case is going to go in the direction that I have it defined, and then what it will do is it will actually apply the same forces in the opposite direction. So it will have those forces arranged in the downward direction, but then also it's going to push up on this frame as well. And then I choose what study to define that to define the load case from. Okay, so that's I've chosen the static study, which is the one that I showed you the setup of previously. So the static study, the stresses from the static study will be used to calculate the fatigue. And then the last thing to do is to define our SN curve. So when I edit the material properties, you can see that we have a stress versus number of cycles curve here that we just enter in the table. Now when you're using steel, SOLIDWORKS simulation allows us to base this SN curve on the ASME carbon steel curve. So because I'm using the plain carbon steel, I can just simply use that value, and it pulls that table in for me. So there are some additional materials that SOLIDWORKS has SN curves for, but most often you do need to obtain those SN curves to utilize the fatigue study. Okay, and then at that point, once we set up the SN curve, our loading event, then we can simply just run the study, and we can get things like our damage plot. In this case, we see a damage of about 40%, meaning that at 20,000 cycles, we're only getting about we're only damaging this about 40% of the total life that it can survive up to. So the damage here in this case tells us that we're not going to fatigue. We'd actually be able to survive this 20,000 cycles. And we can also look at a life plot, and it will actually predict how many cycles it can survive. So if we look at this worst location here and just probe this, if I grab just a location there, you can see that we can actually take about 400,000 cycles at this load case. So that's what this value here means to us. So we can set up the same load case, but it can actually go up to 400,000 cycles before we get fatigue failure. Okay. So jumping back to the slideshow here, the next one I want to talk about is buckling. So buckling is another form of failure that occurs when we have compressive loads. So buckling occurs on slender objects, like you see here. We have this piston rod system, and if we have compressive forces, what's going to happen once we get a high enough compressive force, this thing will tend to want to kind of buckle or kick out, as you kind of see in the animation. So buckling allows us to look at a buckling safety factor as well as the mode shape. The mode shape is just the shape it will take once buckling occurs. Another example is kind of the stool, where if you put a load kind of off center on this stool, you'll see sort of some twist and buckling occur in the legs. So you can kind of see what would happen under this load case. So linear buckling analysis of your design under given loads and supports So again, buckling occurs on compressive loads, and it allows us to look at the buckling load factor of safety, as well as the buckling mode shape, so the shape it will take once buckling does occur. So I've got a buckling example as well over here. So if I go to that, you can see that the buckling setup is very similar to very similar to the static setup, where we're setting up material properties, contacts, and our load case, our fixtures, and then our load case here. So it's actually exactly the same. We have the exact same setup, but this time it's going to use some different equations to solve for buckling. Now, one important thing to talk about within SOLIDWORKS simulation is whenever we have different study types that we want to analyze, for example, I have a static study and then also a buckling study. What I can do is I can create the buckling study, and it will come in empty, and then I can simply just drag and drop these folders. So if I drag and drop, to another study, you can see I can drop them into studies that they kind of qualify for. So I could drag and drop this to the static study or the weld sizing study. So that's what was done. So once you've set up a static study, it's very, very easy to go to a buckling study, because all we need to do is create the buckling study and then drag and drop all these folders to copy everything over, and then go ahead and run it. Now, one additional thing we need to do is set up how many buckling modes we want to solve for. So generally, once buckling occurs at the first mode, then you can kind of get your buckling factor of safety. In this case, you'll see when I run this, we get some negative buckling factors of safety. So what this means in buckling is, if we have a negative factor of safety, it just means if we fully reverse, if we, instead of pointing the forces downward, if we pointed those upward and at the exact, and then increase that 40 times, so we'd have to change all the directions of our load and increase that load by 40 times to have buckling occur. So that tells us that we have a buckling load factor of safety. If we look for the most positive one here is 42, that tells us our factor of safety is 42 times. So if we look at the positive one, again, if this value says if we increase our load 42.896 times, and that would have to be applied to all of our loads, so both the remote loads and the gravity load. If we apply that, if we increase that by 43 times, we will actually get buckling to occur. So that's a very, very high factor of safety, and it is actually much higher than our yield factor of safety, which was just below 2. So that tells us that yielding, because we're looking at a yielding factor of safety in the static study, that tells us that yielding is going to occur way before any buckling would occur on this model with this load case. But if we do ever have, if buckling were to occur, this is where it would buckle. It would be kind of on this leg, and if I animate that, you can see that it would kind of kick out and go to the side there. Okay. So buckling, again, is another form of failure that we can solve for within SOLIDWORKS. Now, another important thing to analyze within simulation is our frequency, our natural frequencies of our structure. So our natural frequencies basically tell us where our what operating frequencies would be dangerous for our assembly. So, for example, if you have a structure that's driving over the highway, generally you want to avoid frequencies between, lower frequencies, say between 10 hertz all the way up to maybe 50 hertz. Okay, so frequency analysis allows us to check all the natural frequencies of our structure, and by doing this, we can get our frequency values as well as, again, those mode shapes, how the structure will sort of vibrate if that natural frequency gets excited. So in this case, We're showing the mode shape of this assembly, and it just shows us that with the fixturing that we have and the mass, kind of the mass distribution of this, we see that this thing will kind of want to rock back and forth if it excites its first natural frequency. So again, this allows us to check for resonance, which can cause destruction if you have dynamic loads, and it should be avoided at all costs. So with our frequency study, we can calculate these natural frequencies of our system and also visualize the mode shapes for the frequency. So the important takeaway with a frequency study is if you know that operating, if you have some data of what the load inputs are going to be, for example, of driving through a dirt field or driving over the highway, generally there's a lot of information out there on load inputs and frequencies that you want to avoid when designing for those environments. And if we check our frequency study, we can actually get the first natural frequency values, and we can design our assembly in such a way that that first natural frequency is much higher than those dangerous frequencies that you have for your environment. Okay. So frequency studies are also sort of the basis for any dynamic studies, any linear dynamic studies that we do. So I'll cover some of the simulation premium capability in a webinar down the road. But frequency study is sort of the basis for that. And if you are getting natural frequencies of your structure that are close to your operating frequencies, then you need to run a linear dynamic study to really look at what those impacts will be if the load is occurring at very high frequencies or frequencies close to the natural frequency. Okay, so I have an example of the frequency as well on this model. So if we look at this, again, we can simply copy and drag and drop these different folders into this, and really we have basically the same setup that we had for our static study. Now, with our frequency analysis, we can choose the number of frequencies we want to solve for, and then if I look at my resonant frequencies here, we can see that the first natural frequency is actually 14 hertz. And then it increases where the second natural frequency is 23 hertz, 57, 87, and then 148. So if any of these frequency values are near the operating frequencies, which 14 probably is in this case, because this is this is for some construction equipment, so usually you want to avoid between 10 and 30 hertz. So we have a couple of natural frequencies that fall in there. So when we look at those values, we can actually look at the mode shapes as well, and we can see that for our first natural frequency, we've got a lot of bouncing up and down. So if we have a load input in the vertical direction at 14 hertz, that's really going to excite our structure here, which is which tells me that we probably would want to run a dynamic analysis on this, because the input forces are the input loads that we'll get from the environment will actually be pretty close to these 14 hertz. Okay, so we can plot the different mode shapes. So the second natural frequency is more in the side to side and kind of twisting motion. So we can see what the mode shape will be at the second natural frequency as well. So we can actually plot those for each of the modes that we've solved for. So again, those types of studies allow us to investigate some additional modes of failure that would occur in deformable body mechanics. Now, there are some additional studies here that Simulation Professional has. The first being a thermal analysis. So thermal analysis is slightly different than what we've previously been talking about, where we're looking at structural loads and fixturing. What a thermal analysis does is it allows us to set up thermal heat sources or temperatures and simulate what the temperature distribution will be in the model. Okay, so we can do a steady state case where we have the load set up, or the thermal load set up, and it basically will run until it reaches the steady state where the temperature distribution is no longer changing. We can also set up a thermal transient study where if we've got if we have different components turning on at different times, we can set up a time curve that says, okay, turn this chip on for so long and then let it cool and then turn this chip on. So we can set up these different time curves and which allows us to see the temperature distribution as a function of time. So here you can see the temperature distribution is changing as our load cases change. And then what we can do, once we solve for a thermal study, once we solve for the temperature distribution, we can also then apply that temperature distribution to a static study where we can look at thermal expansion. So if there's differences in temperatures and where you have different materials and different shapes of structures, you can see that structures will thermally expand in different ways. So you can see in this case when these chips heat up, it wants to sort of expand upward, and you can kind of see it's taking this shape where it's sort of kind of creating this dome-like shape, where we can also look at our once it deforms, we can look at our stresses and see what those look like. Okay, so again, the thermal study evaluates temperature change, both steady state and transient, where we can look at it over time. And heat transfer effects are due to conduction, convection, and radiation, so the three different heat transfer methods. And we can, of course, set it up with time dependency. We can set those values up as time dependent when we run a transient study. We can turn a heat source on and off during analysis using a thermostat as well. So not just time dependency, but we can have something heat up, and then once it gets to a certain temperature, we can have it turn off for a while until it gets down to a minimum temperature and then turn back on again. So we can set up a thermostat much like a thermostat in your house. And then we can also apply contact conditions to simulate thermal resistance. So if you have electronic components, we can simulate things like thermal pastes and things like that, or heat shields. We can set those up with simple thermal resistances between faces. And then lastly, we can combine the thermal and static loading to look at thermal stresses, contraction, and expansion of our models. Okay, next I want to discuss drop test. So drop test allows us to drop an assembly onto a flat surface. It can be a flat surface or an angled flat surface. But with this is actually a simplified dynamic study where we're actually looking at the stresses over a very short period of time. So here you can see this model is dropping from a certain height, or you can set it up with an impact velocity, and you can see that over time this thing will deform, and you can see that it gets those high stresses near where it's making contact with the ground. But you also see areas where the stresses increase up here because of the inertial effects of the mass sort of dropping from this component that's connected in the middle. That wants to keep going down, and you can see that it's stressing here. So the drop test allows us to visualize a very short collision, but again, it has to be with the flat ground or an angled surface. Now we can do collisions between bodies with the full nonlinear dynamic solver available in Simulation Premium. So with Simulation Professional, you get this capability to do this simplified drop test. Okay, and just another example of kind of this camera dropping. So you can see that it's contacting down here, and you can see that this case is sort of sliding open as the latch is holding on over here. Now these plots again they're at a deformation scale, so in reality the deformations wouldn't be as large as we're visually seeing here. They're at a deformation scale to better visualize that. So you know they're probably increased by 10 to 100 times scale. So the drop test in Simulation Professional is there because it's intuitive and easy to perform, you know, a simple drop test. Whereas doing the more advanced, you know, a collision, to do something simple like this in the nonlinear dynamic solver, it takes a little bit more to set up. So the drop test is there to get this small dynamic capability, but allow us to set this up very easily. So again, this calculates our impact results as stresses, deformation, forces. We can also get accelerations and velocities because now we're doing a transient solve where time is actually involved in our equations. And to set this up, we simply just choose a drop height or an impact velocity. We can also do an angle of impact with the surface. We can drop the object on a rigid floor, or we can make the floor flexible so the floor can actually deform a little bit like wood or concrete. We can set up the stiffness of the ground to absorb some of that energy. And then lastly, you choose kind of the impact time. So the time after impact, you know, so it solves a certain number of frames after the impact, so you can actually see the results animated and the stress is calculated at each time step. Next, I want to quickly discuss pressure vessel. So pressure vessel is a capability that allows us to design per the ASME pressure vessel standard. So what this does is it actually takes the software combines existing results as specified in the setup of the pressure vessel design study, where we're setting up different load and static studies, and then we set up a pressure vessel study that combines the stresses from those previous static studies that we set up. So this is in accordance with the boiler and pressure vessel codes, the ASME code, ISO 11439, and the BSEN code. So you know, a lot of these codes are written to do these stress combinations of different load cases, and the pressure vessel design just allows us to set up a different static study load cases and combine those results. It also allows us to do stress linearization, which separates our bending and membrane stresses through the thicknesses of our models, which is actually something that is required for the codes as well. So pressure vessel is useful if you are designing to these pressure vessel, boiler and pressure vessel codes. If that's not your industry, then it's really not. There's really not much you can use it for, but it is there for those that are using it or designing to those codes. Now, just before I finish up here, I want to talk just a little bit about some of the additional tools. You can see here 2D simplification, submodeling, and optimization. So 2D simplification allows us to take our models, and you know, here we have this axisymmetric model. It allows us to simplify it to just kind of this planar value, and then actually revolve all the results around. So you can see the results are revolved around 270 degrees, so we can visually see that. But this is sort of a thermal expansion, you know, between pipes. It's a thermal an expansion absorber, basically. So with 2D simplification, we can do 3 different types. We can do a plane stress where the stresses through the thickness of an object are going to be constant, and then we also have a plane strain where the strain value, so how the body stretches, is going to be constant through the thickness, and then also the axisymmetric, which we saw in the previous example, where we're just revolving the geometry around an axis to give us those. So what 2D simplification allows us to do is it allows us to set up either more accurate studies where we can really refine the mesh on a much smaller body, or we can simply kind of use the same mesh and solve it much faster than it would take than to do it in the full 3D model, or even a model that's based on symmetry. Okay, so 2D simplification capability comes within Simulation Professional. Also, we have a submodeling study within Simulation Professional. So with submodeling, we set up this global parent study, where in this case we have sort of this whole frame, and we have some loading case in the middle here. And then if I go to the next, we can take that middle section and do a submodel of that. So what the submodel does is it allows us to run some global results with a coarse mesh. So it runs rather quickly. And then to set up our submodel, we select the components that we want to include. And then what happens is our global displacements, so the displacements at these locations here on the end of this, they actually get transferred over into the submodel. And it uses those displacements on the submodel, and then also transfers all the loads that would be contained on these bodies. So if you have external forces that you applied or additional fixturing, any of that that's applied would get transferred to this submodel. And then what we can do is we can really reduce the mesh size and get accurate results where they're needed. Whereas we're not really concerned about the stresses out here on this outer frame because they're very low compared here to this middle piece. So running the global results allows us to come up with to easily define our load case. But then we can just carry that over to a much more refined model where we can get more accurate results than what we see with this coarser mesh. And then the last thing one more thing that I wanted to talk about was the optimization. So optimization allows us to basically set up different, again, similar to the motion optimization, we can set up different materials, different dimensions, you can see totally different shapes, different configurations. We can set up the number of instances in a pattern, and you can see how this heat sink is reacting as they kind of cycle through some of these different iterations. So what it allows us to do is set up those dimension parameters or material parameters or suppression states even, and then we can set up constraints on our model. So maybe we want, we want to minimize, or we want to look at the maximum temperature in this model. So that would be one constraint. And then maybe we want to see, well, because we have this thermal, this temperature distribution, we'll have thermal expansion. So then we want to set up as another constraint kind of a maximum value for how much this thing can displace. So then when we have a couple of constraints, what the solver will do is it will run all these different parameters that we set up, like dimensions or materials, and it will run all those and then allow us to look at these constraints, and it will kind of plot it out in a table format here, and then basically it will tell us which one is the best setup based on some goal that we set up. So the goal may be to minimize stress, or it may be to minimize deformation, or maybe it is to minimize the weight. So we can add a mass sensor, to say, okay, we want the lightest one that will be within our constraints. Okay, so design scenarios. So we set up these design scenarios to test a series of designs. So optimization can help to find the best alternative, reduce our time to market, reduce cost, weight, and remain competitive, and also improve product quality. So it allows us to go through many different design iterations or different design ideas in a very short period of time because it's automated. Once you get all the cases set up, all you have to do is hit run, and it will run through those automatically, plot those in a table format, and basically tell you which is the best design. And you can see that it automatically will tell you what the optimized design is based on the input parameters. Okay, so I do have an example of of optimization. If I jump back over to my model here, I've got this one set up. That's the wrong one. Let's go to this one here. So I do have this model set up with optimization, where basically I'm varying the thickness of these side walls. Okay, so I'm changing the thickness of those to, and that can be, you know, anywhere from 0.25 inches to 0.75 inches. So currently they're at 0.75, and what I'm doing, so this one's at 0.75 and this one's at 0.5 to start. So I'm basically saying I can make those between 0.25 and 0.75 at 0.125 inch increments. So it will run all 25 cases of that. And then my constraint is to keep the stress less than 25,000 psi, because that's under our yield stress limit, and then keep the frequency value of greater than 25 hertz. And then lastly, our goal is to just minimize the weight. So if we go back over to the results, you can see our initial case had 14, roughly 15,000 psi and a frequency of 32 hertz. So this was definitely above our constraints, or this was below our maximum stress and above our minimum frequency, but our weight was 288 pounds. So these are very large, heavy steel structures. So then what the software does is it goes through the scenario so you can see the thicknesses change on these. And you'll notice scenario 1 and 2 have the thinner plates, and you can see that they're failing the stress check here. So they're highlighted here in pink. If I click the scenario 3, this one uses a little bit thicker, and it shows that we are accomplishing what we need with those thicknesses. Okay, so then it's basically saying which ones, it's looking for which ones are surviving, you know, based on our constraints, and then lastly it chooses which one is going to have the least amount of weight. So that's actually going to be our optimal design here, which is scenario 3, which reduced our weight from 288 down to 176. And you can see that our stresses remained below 25,000 and also above that 25 hertz. And then with each of these scenarios, we can also visualize the stresses as well. So there's my stress plot, and there's kind of that mode shape, the frequency mode shape that we have. Okay, and then so that's sort of what I had prepared for this. So if I guess if we want, we can open it up to questions here. If anybody has any questions, I'll kind of leave this slide up here.
And we do have a question here, Eric, and I think you're kind of going to be going over a little bit in our next webinar in July here, but we've got a question here. Could you briefly talk about a good approach to select the right kind of linear dynamic analysis while trying to replicate an earthquake seismic effect?
Okay, so yeah, that's actually included with Simulation Premium. So mainly what I've found is if I just go into the dynamic studies, it's what most people do for earthquake studies is most often a response spectrum analysis, and they don't have it here. It is actually included. It's this study here. It's a response spectrum analysis, and I guess it's not PowerPoint. Or random vibration people will often use as well. So the response spectrum is an input the input to the analysis is what's called a response spectrum, and actually the U.S. Geological Survey has a website where you can go and click out anywhere on a map, like a Google map, and it will actually tell us what the response spectrum they have calculated for these types of studies is at really any point on Earth. So what I've found is we can do the response spectrum analysis. We can use that map to find what our inputs are at that location, and then just simply apply that to our model. And then again, the same types of things apply where we need to set up our fixtures and our contacts between the structures. So if you want more information on that, I would suggest you do a little searching on response spectrum analysis. And then I have seen in a lot fewer cases, sometimes random vibration analysis will be what people use with earthquake analysis as well.